So thank you for being there. Uh, my talk is about implementing MD5 collisions on a GPU, video card GPUs, or graphic processing units. I'm going to talk about first a short reminder about how MD5 works and why it is why it is a very good algorithm to run on GPUs. And then I'm going to quickly explain what happened in December 2008 when a group of researchers published rogue CA based on by using an MD5 collision. And then you have to know that the most computing intensive part of that attack is something called the MD5 birthday search. And finally, I will show you the results and performance numbers that I have obtained. So MD5, it's important to know that this is it has been optimized for 32-bit architectures. It only uses 32-bit integer and logical instructions. And what we call general purpose GPU technology is a flexible framework that allows you to run any code, arbitrary code on GPUs. You can really, few people know that, but GPUs are able to execute integer, logical, floating point, even control flow instructions. You can pretty much do anything. It doesn't necessarily mean that what you implement on GPUs is going to perform efficiently, but if you have a workload that is able to exploit the performance of GPUs, it's going to run very quickly. And the reason for that is because GPUs are massively parallel chips with lots of arithmetic and logic units, or LAUs. The reason they are based on a massively parallel architecture is because video card processes pixels, and the process is graphic rendering is based on the fact that each pixel can be rendered independently from each other. So this is really important to understand the level of parallelism that exists on the GPUs. Typically, in a single clock, a modern GPU can execute hundreds of instructions per cycle, as opposed to a regular quad-core processor that can execute up to 12 instructions in parallel, 3 per core. And we have seen the GPU technology gaining ground recently, but I don't think that most people realize the power of these cards. So one of the objectives of my talk is to really raise awareness of GPUs. I focused my work on ATI GPUs because the latest family of ATI GPUs, called the R700 family, the commercial name for that is the series of cards, Radeon HD 4000. These GPUs have up to 800 LAUs or SPUs per chip, and they are clocked at typically around 600 up to 850 megahertz. And as most of you probably know, you can buy dual GPU video cards, which would bring the total number of instructions you can execute per cycle to 1,600. Now, if you look at the technical characteristics of ATI cards, you will notice that the one providing the best performance per dollar or performance per watt ratio is the ATI Radeon HD 4850 X2. I have one with me right there. This is what it looks like. Standard dual slot PCI Express video card. It costs about $200 and consumes about 230 watts of power at full load. And the next ATI generation is going to be the R800 series, which is going to come out in 2 to 3 months. I'm really impatient to see what these are capable of, but according to the latest rumors, these R800 chips might provide up to 2 or 3 times more performance than R700. Why I did not choose NVIDIA is because if you look at even their top-of-the-line card, the GTX 295, it can execute only up to 600 billion instructions per second, as compared to 1 trillion 32-bit instructions per second for the HD 4850X2. So it's about half the performance. If you look at the price, it's also like twice more expensive. And overall, it's not the best choice if you want to run GPU workloads. However, the NVIDIA SDK, known as CUDA, is very well known, very mature, very easy to develop with. That's why most people choose NVIDIA cards when running workloads on video cards, just because the SDK make it much easier. Now, to go back to the main topic of that talk, in December 2008, this group of 7 researchers implemented what is known as an MD5 Chosen-Prefix collision attack to create a rogue certificate. They used a cluster of 215 PlayStation 3s, and according to them, it took 18 hours to perform the most computing-intensive part of that attack on their cluster. So this is, I try to summarize what they did in one slide. It's very high level, very simplified, but basically, they came up with a way to create certificate A, a legitimate certificate A for some arbitrary website. And they built a rogue CA that I call B in a way that the MD5 hash of these 2 certificates collides. And then they had the public CA sign a certificate signing request that ended up producing the certificate A, and that allowed them to steal the signature of A, apply it to B, and make B a valid certificate. So this is there are like dozens of details that I'm just not going to explain there, but basically it involved being able to predict the serial number used in the certificate in certificate A to be able to mount this attack, and there were a few other details to take care of, but basically. Once the hash collides, you can get a signature and apply the signature to another certificate to make it valid. So this attack consists of 2 stages. The first one is called the birthday-inked stage. I'm going to explain a bit later what this is about. The second stage of the attack is called a near collision stage, where basically the birthday step creates data that is almost colliding, but not quite yet. And the near collision stage consists of just adding a few blocks of data to the certificates to make them collide. And the first one is the most computing intensive part of the attack. That's the part I decided to focus on. So what MD5 birthday is, very roughly speaking, you start by creating arbitrary data to 2 certificates called bit strings there, and when you process these prefixes through MD5, you end up with 2 different states. MD5 internally tracks the state of the current hash computation in 4 variables named A, B, C, and D, and the goal of birthdaying is just to append a small number of bytes to these prefixes, such as the 2 states are somewhat related. So, for example, the value of A in the 2 certificates has to be equal, and there are other constraints that apply to B and C and D, but I'm just going to skip the details because I don't have enough time to talk about that. But basically, MD5, the MD5 birthing stage consists of just brute forcing this small number of bytes that you append to the certificate to end up finding basically two states that can be used to build that collision. So it's just a brute force step. You append some random bytes, and you compute MD5. If you are happy with the stage, you keep it. If not, you continue. So optimizing that phase only consists of coming up with a good implementation of the MD5 compression function, which is the main part of MD5. So I wrote an MD5 implementation in something called CAL-IL. It stands for Compute Abstract Layer Intermediary Language. It's a sort of a pseudo-assembly language that can be used to program ATI cards. It doesn't reflect the actual hardware instructions executed by ATI GPUs, but it's pretty close. And the reason I chose this very low-level language is because it's the only way for me to really be able to fully exploit the performance potential of GPUs. ATI has something slightly higher level called Brook Plus, which is which has a C-like syntax, but it doesn't really allow me to do everything that I needed to do. So this is a screenshot of what MD5 looks like in CAL-IL. I didn't write that code myself, but I wrote a Perl script to generate that pseudo-assembly code. So basically, you can look at my white paper on the Black Hat website to see what kind of tricks I used to optimize MD5, but it's very basically, it consists of mapping the MD5 steps to the CAL instructions, and I use tricks like using multiply and add instruction right there to simulate, to execute rotate in 2 instructions instead of 1. I don't have much time to explain more about it, but basically the results I obtained were about 1.6 billion MD5 hashes that can be computed on the HD4850X2 card. And I have noticed a potential optimization that would allow me to compute up to 2 billion hashes per second, but I have not yet tested it, so we will see. But basically, what this means is that if you take two such cards in a single machine, that would give you 4 GPUs, costs a bit less than $1,000, with a power consumption of 500 watts, and that server would be able to compute up to 3.3 billion hashes per second, so 3.3 billion calls to the MD5 compression function. So I built that server as an experiment to see if it was feasible. I am a cheap guy, so I actually didn't use a motherboard card with 2 PCI Express X16 slots, but instead I used these flexible PCI Express adapters, so to allow me to put the cards on PCI Express X1 slots. There were numerous issues I had to work around to make this work, but basically some motherboards allow you to put X16 cards into X1 slots. This is called downplugging, but not every motherboard allows this. And I got access to the PCI Express spec and noticed that basically you have to make contact to short pins A1 and B17 to fake the presence, to basically make the motherboard believe that you are plugging in next one card. So that's a trick, as far as I know, that nobody knows. If you look at forums, video gaming forums, you can see people trying to put X16 card into X1 slots. For a lot of people, it doesn't work. Well, you have to short these 2 pins. That's how you do it. And one thing you have to be aware of is that the current ATI Linux drivers doesn't support more than 4 cards per server. So I was planning to start playing with the PCI pass-through feature of KVM and Xen to assign 2 GPUs, 2 video cards to a virtual machine, 2 video cards to a second virtual machines. But it's not quite stable yet. It doesn't really work. The code is still being worked on by Xen and KVM developers. So maybe it's going to work in a few months. I don't know. But basically, if you compare solution based on GPU servers with the cluster of PS3s that the 7 researchers used in December 2008, you end up noticing that GPUs can accomplish the same amount of work while consuming 1/5 of the power and being 10 times cheaper. So it's an order of magnitude faster per watt and per dollar to do that on GPUs. Now, one additional tool I am going to release next week. I am going to open source my code and publish it on my website next week. But with that MD5 implementation, I can do something that others try to do. I don't know if you guys remember, but a while ago, Nick Breeze published code that was supposedly reaching 1.4 to 1.9 billion MD5 hashes per second on the PlayStation 3. He was trying to basically brute force MD5 hashes because some web applications that use unsecure, unsalted hashes tend to default on MD5. That's why you have that people working on the MD5 brute forcers, because when they come across MD5 hashes, they have a need to crack them. So Nick Breeze supposedly reached that number, but it turns out that the benchmark program he wrote was not using the value computed by the loop. So he was actually benchmarking a loop, an empty loop running on the PlayStation 3 processor. And after fixing that bug, he noticed. So he got a lot of. There was a lot of buzz around that figure of 1.4 billion hashes per second. But with the MD5 implementation I wrote, I actually do reach 1.6 billion MD5 hashes per second on the video card. And one possible optimization called MD5 reversing, which consists of basically not computing the last 15 steps of the MD5 compression function would allow me to reach up to 2.2 billion MD5 hashes per second, which makes it the fastest MD5 brute forcer ever. So that talk basically demonstrates that MD5 Chosen-Prefix collisions can be performed by anybody. You don't need a cluster of PlayStation 3s to execute them. I was told 2 days ago that by Mark Stevens, which was the researcher that came up with the idea of Chosen-Prefix collision, that they started implementing a version of MD5 Chosen-Prefix collision attacks using the NVIDIA CUDA framework. So I am most likely going to help them port my code to their framework to basically have this open source tool that would work on NVIDIA cards and ATI cards as well. But one thing I really want to emphasize is that if you have a workload that runs well on GPUs, they are just so effective, so fast that it doesn't make sense to consider anything else. Even a cell processor or even some FPGAs. If you look at that, I have like one of my side projects is to compute rainbow tables for the GSM A51 encryption algorithm, and I already reach, according to some estimations, this card is able to beat the FPGA that Hikari was using back in 2007, I think, to build his rainbow tables. So that's, in my opinion, GPUs are going to become the next standard for computing intensive workloads. So check out my website next week. It will be updated with the code and the doc. That's about it. Thank you. Any question? Yeah. So this cluster of 215 PlayStation 3s took 18 hours to generate, to complete the MD5 birthdaying stage. However, the group of researchers that published that technique found like theoretical optimizations, and they published various improvements that would make it possible to generate a Chosen-Prefix collision in less than a day with a video card or even a regular processor. I'm sorry, can you repeat? Can you repeat your question?
Usually when you're looking at electrical space, you say left side shots in half of it, there's a 50% chance that it has.
Yeah.
You're saying a day, would that reduce
Yeah, it's the 50% mark. Yeah, the question was typically when brute forcing something, you have to cover the full key space, but if you cover only half of the key space, you have a 50% chance of having succeeded the brute forcing phase. So in a day, you have a 50% chance of having successfully generated an MD5 collision. That's the answer.
What about SHA-1?
I believe that SHA-1, I know that SHA-1 is also just perfect for GPUs. SHA-1, even recently the same cluster of PlayStation 3s was used to break key used by an elliptic curve cryptographic algo, and this algorithm would also be just perfect for GPUs.
Is that something you're going to work on?
Maybe. I have lots of projects. Yeah.
How long did it take you to implement the MD5?
It took me about 2 or 3 days to implement MD5 for the TI GPU. Thank you.